in with Andy Maida at NYU. And actually, I spent 3 years in NYU, not one. So that's the anecdote you can use. So the story is that I actually started my postdoc 2 years before I finished my PhD, which is don't tell that to my advisor. Okay, so this joint work with a few people. So there are 3 there, but there are many others that I don't have space to list here. These are the main people who would work on this at NYU Abu Dhabi. This is the new campus that NYU have. So they have a center for prototype climate modeling where so Andy and 2 of his colleagues created this center. And then we've given lots of resources so we could try all the ideas we worked on when I was a postdoc with him to try them in these big climate models. So Chang Deng is a postdoc there, and he's basically the guy who did all these computations that I'm going to show today. Ajaya Mohan is also there. He's a senior scientist. So this work is also funded by the Indian Institute for Tropical Meteorology Monsoon Mission, because they are interested in these models. They want us to put them in their climate model, and we are working on this right now. So this is the outline of my talk, and basically I'm just going to give you some idea what's tropical convection, why we are interested in it, what kind of models we are using, mostly stochastic multi-cloud models they are called, and I will show you some simulations of some intraseasonal oscillations in the tropics, this kind of intraseasonal oscillations that climate models have actually hard time to capture. So this work is in these 2 papers, at least what I'm presenting today. One of them is already in press, and the other one is just submitted. These are disciplinary journals, and they're not math papers. But forgive me, I'll try to give you some math, but my talk would probably be a lot of meteorology. So why are we interested in the tropics? So the main reason is probably the last one. Climate models perform very poorly in the tropics. And the reason is basically what's first. So tropics are important because that's where all the energy for the Earth system comes to. And then it's spread to the rest of the globe through atmospheric and oceanic circulation and waves. So tropical dynamics is very complex. And the reason why it's very complex is because of the Coriolis force that acts on the atmospheric flows and oceanic flows vanishes at the equator. So you know that cyclones spin counterclockwise in the northern hemisphere, but they actually spin the other way in the southern hemisphere. And at the equator, you have a 0. So then that creates kind of an asymmetry or some kind of a region that's very particular, or kind of a singularity, if you wish. But this makes the equator a waveguide for a menagerie of waves. There is a whole spectrum of waves that live on the equator, and they are not actually, that don't propagate outside. But there are other waves that create strong interactions between the tropics and extratropics. And there is also the other thing important, because the tropics are warm, the tropics have lots of convection. Convection creates lots of scales. There are lots of scales from the scale of the cloud of a few kilometers to the planetary scale of like 20 to 40,000 kilometers. You have waves of different scales, and they interact with each other. I'll try to give you some flavor of all these things through my talk. So this is just like a satellite picture of the clouds, the distribution of clouds in on the Earth. So what you see, you have basically three regions of cloudiness that are very visible. There is the equatorial region, that's the tropics, and there are these mid-latitude regions, north and south. These are just basically the mid-latitude weather systems that where we live in. But then the tropics, you can see the distinction between the clouds in the tropics and the clouds in the mid-latitudes. So one of the main distinctions is that the clouds in mid-latitudes are kind of smooth and nice. And in the tropics, you see lots of scattering, lots of randomness. And the reason behind that is because in the mid-latitude, the clouds are actually slaved to the dynamics. And the dynamics are these giant Rossby waves. These are the big cyclones you see on the weather map. These are known as Rossby waves. These are the ones that actually predict the weather. So when you see these waves on the weatherman, it will say, we have a low pressure system, it's going to rain. It's mostly always the same, true. In the tropics, it's not that way. It doesn't work that way. In the tropics, the clouds and the circulation actually interact with each other. And the clouds organize at different scales. And that's why you see all that patchiness. And because of that complexity, the tropics are very hard to capture by climate models. Because climate models use mesh sizes that are grids that are very, very large, around 100 kilometers. And your clouds are about a few kilometers. To get the interactions between the clouds and the circulation, you need to resolve these scales. But of course, it's not possible. So you have to figure out how to model these interactions. And what we do, we use stochastic models for that. So this is just to convince you that the tropics are important, especially for this region of the globe. This is what's known as atmospheric rivers. What you see on the movie there is water vapor distribution. But you see these filaments that come out of the tropics and they hit the coastal areas. So you see a particular one in this region. There is this one that would hit the Pacific Northwest. These are known as the Pineapple Express. This is the one that brings, so just yesterday, you have lots of floods in Los Angeles, in California, and so on. And this is one of those. So all these things are actually triggered from tropical stuff. And there is this nice paper by Ralph and other people where they actually trace these atmospheric rivers to things. These are waves in the tropics, known as MJO, Madden-Julian oscillation, Kelvin waves, and so on. These are the beasts that actually live in the tropics that climate models have hard time to capture. So this is just a satellite picture of this is outgoing long wave radiation. If you can just think of it as just cloudiness, and it's averaged north-south from like 2.5 south to 7.5 north, and this is just the space that's the zonal, just the longitude on the x-axis, and time on the y-axis, and time goes down. So what you see a big blob of clouds propagating eastward. That's known as the MJO, the Madden-Julian oscillation. It propagates like 5 meters a second, and it lives mainly in the Indian Ocean, Western Pacific region. And then you have other stuff that are the Kelvin waves that also propagate eastward and propagate faster. These are the ones that are shown here. This is the MJO, and these are the Kelvin waves. So this is just a spectral view of these waves, just a Fourier analysis. So now we have wave number that represents the east-west propagation, and then you have the frequency of or phase, if you want, on the y-axis. And you see all these different waves. So the major ones, of course, are the Kelvin waves that we saw, and then we have the Madden-Julian oscillation. The straight lines on the other lines you see there are basically just solutions to the shallow water equations on the equator. You get the solution, the wave solutions. These are the known as equatorially trapped waves. And these are the dispersion relations of these waves. What you see spectral peaks of this observed cloud streaks or blobs or whatever you want to call them. They actually project on all these solutions except for the Madden-Julian oscillation. The Madden-Julian oscillation doesn't live on any of these waves. And that's a phenomenon that's completely poorly understood until now, where it comes from. So there is lots of theories that say that actually the Madden-Julian oscillation is nothing but an envelope of the other waves. Okay, so just to convince you that climate models are doing a very bad job on these things, this is the IPCC report, the last one. This is the International Panel on Climate Change report, the last one, the fifth. It came up in 2013. So let's see what they say about all these things, about the MJO and all tropics. So they say that there are biases in the IPCC models, especially in the tropics. So just look at the red points there. That's basically, there are lots of biases, but let's just focus on these ones. They say that despite the apparent skill, many models individually display substantial precipitation biases, especially in the tropics. The precipitation distribution along the ITCZ. The ITCZ is the kind of the white, very bright place you see there. It stands for Intertropical Convergence Zone. That's where most of the tropical rain is actually, you can see it. So you have the Indian Ocean, Western Pacific, there where it's centered, and then it shifts north, and then it shifts south. Climate models have a very bias there already, because like there is a southern ITCZ that's kind of very parallel to the northern one, but in observation, it's not like that. ULCL, so it's not very bright in the models in the Indian Ocean. This is kind of biases you see there. So as I said, clouds and precipitation are unresolved processes, and they are associated with synoptic and transitional weather systems. So this is why they are very complex and why they are important. So the convection, there is a vigorous flow associated with it, so you cannot just ignore it. So these organized systems, so they have all this various, sorry. So as you see, so if you want to resolve everything, you have to go to like 100 meters resolution. That's really not possible for climate models. So we need, what we do, or what people do, is something known as parameterizations. So parameterization is basically, you write a very simple model to represent the convection, and that simple model with feedback into your GCM, the climate model. So early parameterizations, one of the big problems with the early parameterization, or at least traditional parameterizations, if you may, they represent clouds in a very kind of not optimal way, in a sense that it's not what the observations tell us that this parameterization do. So most of the parameterizations just fire up convection very quickly and to the top of the troposphere. But observations in the tropics revealed that actually there are many types of clouds. There are essentially three types of clouds. There are the shallow clouds, and the mid-level clouds are called the congestus clouds, and there are the deep clouds. And on top of that, there is what's known as stratiform clouds. Stratiform clouds are these anvils you see on top of the big towers there. So traditional parameterizations, what they do, they just try to represent these big towers. They don't represent the other cloud types. So when you don't represent the other cloud types, you basically, because, well, there is one reason why they do that, because these big towers are the ones that are responsible for most of the rain. But the other cloud types are important because the clouds interact with each other. And the different cloud types help the organization into multiple scales. Well, how it happens, because the lower clouds, although they don't precipitate, the lower clouds come up when the atmosphere is dry. So what they do, they precondition the atmosphere. So they moisten it. So they detrain their moisture. And then when the atmosphere becomes moist, then you start getting the deep clouds. The traditional parameterization don't have these congestus clouds. So what they do, even though the atmosphere is still dry, they fire up convection. So there is like a phase delay that's missing there, and it's very important for the fluid dynamics. It's very important for the interaction with the waves. So this is just a picture of a mesoscale system that has all these cloud types in it. So what you see in front, you have these congestus clouds that actually moisten and trigger some convergence to the center, where you have the deep cloud, where actually you have a raising motion. But then on the back, you see the stratiform anvil. The other important thing about the stratiform anvils is that they have this downdraft. So there is rain that comes down. The rain evaporates there. When it evaporates, it cools the atmospheric layer there. The cold air will sink. It creates downdrafts. And these downdrafts, you cannot capture them if you have only one cloud type. So that's why we need the stratiform part of the cloud. So these are known as unsaturated downdrafts from the evaporation of stratiform rain. And my talk today is basically just to tell you how these stratiform clouds are important, how these downdrafts are important for the planetary scale organization of convection. So there are a few people who worked on this who basically said that stratiform clouds are important. So they are important because they are observed all the time. When there is organized convection, especially like convective systems, people say these stratiform clouds are always there. They induce this mesoscale overturn and circulation I showed you. These downdrafts, then feedback, and then you get this mesoscale circulation. They create gravity currents in the boundary layer. And these gravity currents you see there on the boundary layer, they go and they kick out new convection, basically. That's what they do. So then that's actually lead to propagation. So the system then can propagate because of the stratiform. There are lots of other work. So there is work that actually say that this stratiform cloud allow the system to tilt. And the tilt of the system makes the whole heating to project on vertical modes other than the deep mode that's responsible for very fast waves. The shallower modes move slower. So then you get slowdown of the waves. So that's an important phenomenon also we worked on. And there is this theory of stratiform instability. When you put the stratiform clouds in a very baby model, you come up with an instability of waves at synoptic scales that's been tuned, that's been known as the stratiform instability. So I'll pinpoint to the math and to the parameters where all these things are coming in a few minutes. So the multi-cloud model we designed looks like this. This is just the cartoon. So it has all these cloud types, the shallow, the congested, the deep, and then the stratiform. And then we allow the different pieces to interact with each other depending on the environment. And this model, we worked on it a lot. It was able to simulate convectively coupled waves, the Madden-Julian oscillation, and all lots of things, and with very, very great success. So now what we're trying to do is to make a stochastic model for the clouds. And then the stochastic model, so you can actually now patch it to climate model. You have your traditional cumulus parameterization that doesn't care about these clouds. But you can hook the stochastic model onto it, and then it will tell the parameterization when it can fire up convection, when it cannot, according to the prediction of the multi-cloud model. The multi-cloud model is based on a lattice. So we put a lattice on top of the GCM grid. And inside each lattice site, we allow convection to happen and to be of certain type, either congested, deep, or stratiform. And then or it's a clear sky site, there is no cloud in there. Then we make some intuitive rules how to transition from one state to another. So a clear sky site will trigger a congested cloud if there is an instability. CAPE is just an instability for convection. It means the boundary layer is very warm and very moist, and the upper troposphere is cool and dry. Then you have lots of instability. Then you make these congested clouds. But we don't make deep clouds unless the atmosphere is moist. So if the atmosphere is dry and there is instability, we make congested. If the atmosphere is moist and there is instability, we make deep clouds. And then the deep cloud will become a stratiform cloud in the future with high probability. And then all the clouds are allowed to decay back to zero, to clear sky. And what you get, this is basically just a particle interaction system. It's a huge Markov chain that lives on that lattice with state 0, 1, 2, and 3, depending on the cloud type. And the state space is huge, as I was telling you. And any configuration or any element of the space or realization is called a configuration in this jargon of this particle interacting systems. And then we make spin flips, or if you want, or we make transitions from one configuration to another. Or you make a configuration at one site, you will just go from one state to another by adding some number eta, and that's a random number. So we allow some natural transition to occur, and others are not natural, so we don't allow them. So we allow transition from clear to congested, from congested to deep, from deep to stratiform, or from congested to clear, and so on. And we allow other, of course, that are associated with eta equals 1 or eta equals -1. And then we have eta equals 2, -2, and -3. These are all possible. But that's all we allow. So of course, then these are just Poisson processes, if you wish, and each one of the processes is associated with a transition rate, and the transition rates will just be functions of the large-scale state. They will be functions of the instability and the dryness of the upper troposphere. If the upper troposphere is unstable and it's dry, you make congested. That R01 is the rate of transition from clear sky to congested. And you have 7 rates, and they all depend on, you have time scales that we basically just set values intuitively according to some intuition, how these clouds actually, what's the time scale of this formation of these clouds. But we also have developed some Bayesian inference, like inverse problem inference algorithm, how to use data or simulations of clouds to infer these parameters. So that's done. We can do that. And this, now what we want to do, so we want this to be, this is basically, it's a particle interaction system. It has a Hamiltonian. It has, you can compute a Hamiltonian. You can make up a Hamiltonian so you can minimize that Hamiltonian and you get an equilibrium, Gibbs canonical equilibrium measure. And then we want this dynamics to make up to be consistent with this Hamiltonian structure. So then you want this Markov chain to converge to this equilibrium measure. And what you do, you just basically impose detailed balance. That's one way to do it. And of course, we cannot do exact detailed balance, but we can do something we call semi-detailed balance, but it's enough to get this measure to converge to the equilibrium measure, the Gibbs canonical measure. And then the beautiful thing about this, now you have all these clouds that bubble in the small lattice, on this lattice with high resolution, but you don't need to resolve this lattice because we can write down a stochastic model for the coarse graining of this lattice. So now we are just interested in the area fractions of clouds, of each cloud type in each GCM box. So you take a GCM box, the thick line, you count how many clouds you have of each type in each side. These are the area fractions. Then you can write down a birth-death process for this area fractions. And this birth-death process can be run very, very cheaply. Like it's just, you just need to select 2 random numbers at each clock time. So you just move on with 2 random numbers, and it's very cheap. It's the overhead is very insignificant. If you compare this to doing this as resolving clouds, real clouds, it's really, it's no-brainer. This is much, much, much cheaper. It's orders of magnitude cheaper. Then we assume that each one of these cloud types is associated with a heating profile. This is how convection happens. So the deep clouds warm the whole troposphere. They have a sign profile like that. The stratiform clouds warm the upper troposphere and cool the lower troposphere. The congested clouds heat the lower troposphere and cool the upper troposphere. And then we have this amplitude functions for each one of the cloud types that are computed directly from the instability and from the moisture availability, but also they have the coefficients sigma C, sigma D, and sigma S. These are just the area fractions from the stochastic model. Now, today I want to talk about the effect of the stratiform fraction there and the effect of the stratiform coefficient alpha S there in red. How much stratiform do you need to make an organized system at the planetary scale? How much stratiform you need to make an organized system at the synoptic scale, which means like 5,000 kilometers versus 20,000 kilometers. So this is basically the main question. So the other key parameter is, as I said, you have the boundary layer. So the boundary layer is the downdraft act on the boundary layer through the stratiform. So the stratiform creates downdraft mass flux that cool and dry the boundary layer. So theta EB is just the potential, equivalent potential temperature, which means temperature rescaled with pressure plus moisture content in the boundary layer. And the minus 1 over HD, that's what cools and dries the boundary layer. But the D forcing term depends on the stratiform heating, and there is the mu factor there. And that's the mu that creates the instability that's known as the stratiform instability. Well, when the mu is not present, you get basically no instability in the system. And now we are going to see how mu is important for climate model simulations. Okay, so I'm going to show you some simulations on an all water world. Okay, so there is no land, there is no topography or anything else, and there is no ocean coupling either. I'm going to impose something known as the warm pool. So the warm pool, these are just the warm waters in the Indian Ocean, Western Pacific. As you see on the top picture, that's just an observation of the surface distribution. So you see that warm waters in the middle, in the maritime continent around north of Australia, and they are in south of India and China. So this warm pool, we represented in our model with this cosine function like that. So remember, now we are going to do the numerical experiments, and we are going to look, remember this is the observation, how to unpack the modeling of observed spectrum, how we get the MJO versus the Kelvin waves mostly. So these are the experiments with alpha S equals 0.5 and tau 30 equals 5 hours, which means this is the time scale at which stratiform clouds die. Okay, that's 5 hours there. And alpha S is just the coefficient in front of the stratiform heating. So what you see on the top is just the typical simulation. This is the heating, the deep convection, congestus, and stratiform. What do you see? You see this oscillation at 40 days, which is exactly the Madden-Julian oscillation. So you see the spectral power there at 40 days in all this, and he has that dispersion relation that's horizontal, just like the observed MJO. So this is the MJO regime. If we lower alpha S, that's the coefficient of stratiform heating, what we get something different. You get very fast waves, faster waves, more frequent, a period of like 5 days instead of 40, and with that spectrum there, that is just follows the dispersion relation of Kelvin waves. So more stratiform gives you MJO, less stratiform gives you Kelvin waves. On the bottom, the experiment 3, it should be 3, not 2, we kept alpha S is 0.25, but now we raised the death rate, or the death scale, the time scale of death to 10. So we decreased the death rate. So the time scale of death is 10 of stratiform. What happens? We go back to the MJO regime. You get an MJO back. So again, if you let the stratiform clouds to live longer, it's the same thing as letting them to be stronger. So it has the same effect. So what happens, because the stronger stratiform anvils, or the longer they live, the stronger the downdrafts they produce, and the stronger they act on bigger areas in the boundary layer, the regions on which they shut off convection in the boundary layer and trigger this gravity current, the scale will be different, depending if it's smaller or larger, if it lives longer or it lives shorter. That's important for the time scale at which they reproduce these downdrafts. To see whether this is exactly what happens, I'm going to act on that mu parameter. So now if I just act on the mu parameter, with mu equals 0.1, you still have an MJO. With 0.05, the MJO is kind of starting to, it's still there, but not as good as in the beginning. But now with 0.001, your MJO is destroyed, you are back to the 5-day oscillation. So it's the downdraft that's one of the most important effects. So that's what happens here, and the MJO scale is this stratiform instability that's been discovered many years ago, is the one that acts on the preferential scale of Madden-Julian oscillation. How much time do I have? 4 minutes, okay. So I'm just going to show you similar results, but now for the monsoon, for the Indian monsoon. So the monsoon is basically what happens in the summer. The tropical convergence zone moves northward in the summer. As it moves like that, it creates this monsoon where we have lots of rain in India. But the monsoon has its own intraseasonal oscillations. And the intraseasonal oscillations in the monsoon move south to north instead of west to east. Instead of moving to the east, they move northward. And one of the big challenges of climate models is to predict this northward propagation of rain, because it's really important for India. Because when this rain propagates, then it shuts off, or it goes on. When it shuts off, it's known as a dry spell. When there is a dry spell, if it lasts too long, then you have no rain in India, and then they starve. There is basically just the economy will go down. Agriculture will just die. But if there is too much of wet spells, you get floods. And the climate models are enabled to produce these intraseasonal oscillations. And to this, there is also westward propagating weather kind systems in the monsoon trough at the same time. The monsoon trough is that circulation of air that goes and then hits the Arabian Sea and goes to Somalia and comes back. That's called the Somalian jet. And that's the monsoon trough is north of that jet. So basically, that's where all the activity happens. So this is the model simulation. So we capture that monsoon trough, especially when we put the warm pool at 15 degrees or at 10 degrees. We capture that trough. The colors are the vorticity. The trough is when the vorticity is positive. You get this giant anticyclone. But we also capture the northward propagation of the intraseasonal oscillation, especially at 10 degree north. You see it, how it propagates. At 15 degree north, what we capture is westward propagating systems. These are known as the low pressure systems, are very important for the weather in the Indian Ocean. So what we see, the ability of the model to reproduce northward propagation system or westward propagation synoptic systems depends on that parameter alpha s. With alpha s equals 0.5, what we get is mostly these northward intraseasonal systems, just like the equivalent of the Madden-Julian oscillation. But as you go to alpha s equals 0.125, that northward propagation disappears. If you see the bottom panel, there is nothing there at 40 days. But you see on the upper panel, you see lots of stuff moving westward. And these are the low pressure systems. And these are also very important as they bring lots of rain from the Bay of Bengal towards India. And when these systems are not present or they are not well simulated, it's very hard to predict the weather in India. So this model predicts well the weather, and we kind of think we understand why you get low pressure system versus the intraseasonal oscillation depending on the stratiform portion. What the stratiform portion makes a difference, it makes a difference in the shape of the trough. The monsoon trough is the red color you see there on the right, on the left panel. And 10 degrees, that's the trough, how it looks like no, not 10 degrees. At alpha s equals 0.5, alpha s equals 0.25, and alpha s equals 1.125. That's the monsoon trough extends. And this extension is associated with the westward propagation of this synoptic scale systems. In the other regime, where you have northward propagation, you have only that northward propagation that helps the monsoon trough spreads northward. If you see the top line, the red color goes this way. In the other ones, it goes that way. This is the mean. This is the average like a system. So this is the trough of the monsoon. I'm just going to stop with this figure. So this figure shows you a comparison of the shear between the 3 simulations and the observations. So the red is alpha s equals 0.125. The green is alpha s equals 0.5, and the blue is alpha s equals 0.25. So, and the black line is observations, is reanalysis data. So what we see is that the shear, at least in the troposphere, where the model actually, in the stratosphere, we are doing nothing, basically. So in the troposphere, you see the shear at 1.25, where the low-pressure systems live, matches with the observations. And what the observations show, we show lots of these low-pressure systems. And also the vorticity, on the other line, the observed vorticity, so when you shift from the lower vorticity is cyclonic, and the upper vorticity is anticyclonic. And the point where you shift from cyclonic to anticyclonic, you see it's not the same in the red curve and the blue or green curve, but the red curve matches the observations. They switch at the same level. And the observed structure of this low pressure system is well reproduced with our model, although the resolution is 170 kilometers. And the systems are like, well, they are like 1,000 kilometers. So it's less than 10 grid points. But we still get very good representation of the dynamics. You see this warm temperatures above and cool temperatures below. Climate models are no near of representing something like this. So I'm going to stop here. Thanks for listening.
Time for one question, maybe. If there is one.
Curious about the Markov model.
Yes.
Is it an absorbing Markov thing? Is it exotic?
Absorbing?
Yeah. Does it have a steady state, or do you think it captures?
Yeah. It's ergodic.
Is it exotic?
Yes, it is ergodic. What's that?
What's the steady state?
The steady state is the Gibbs canonical measure. You're welcome.
All right, I think, thank you again. I have one quick announcement to make. So all the speakers and everyone who's from funding too, could you please go to the registration desk to fill out some paperwork. So lunch, there are several options here. This is campus, so we are there, the red star.